Łukasz, the screen is yours.
Thank you very much. Thanks for the introduction and for the invitation. It's a pleasure to be here. And the amazing story is a story of basically one theorem that we with Jan Derbisz, Tomasz Krawczyk, Jana Nowotna, and Karolina proved, which is a theorem stating that vertex deletion problem into bipartite permutation graphs admits an FPT algorithm. And the title pretty much tells all about the structure of what I'm willing to show you. So first of all, I'll speak a little bit about vertex deletion, then about bipartite permutation graphs, then about our theorem, and then about its proof from a high level. But I want to let you feel the flavor of the conceptual layer of everything what's happening there. So if we have some time left, I'll show you some proofs as well, like more detailed ones. And for the technical stuff, I don't know what the convention usually is here, but if you have any question on, or if you think that I'm saying anything inappropriate or wrong, it may happen. Don't hesitate to unmute yourselves and ask whenever you want. Don't wait until the end. It's I mean, I'd love to interact during the presentation. Okay, so let's start. First of all, vertex deletion, as promised. So let me quickly recall what it is to those of you who know, and introduce to those of you who don't know that much. Suppose we have a graph and an n-vertex graph and a graph class, which is our favorite graph class for some reason. For example, because it admits better solutions to some problems that are hard in general. And because this graph class is our favorite, we want to modify our given graph in order to obtain a graph from a class. More precisely, problem of vertex deletion, we want to delete the smallest number of vertices in order to get a graph which belongs to our class. And speaking of vertex deletion, it's always a good idea to consider not just a graph class, but a hereditary graph class. So a graph class which is closed under vertex deletion, so that after we fall into this class, we don't go out of it. And it turns out that for hereditary graph classes that are non-trivial, so in some sense infinite, so they don't trivialize, the problem of determining the smallest size of the vertex set to be removed is NP-complete, which gives rise to restate the problem in parameterized way. So now let's have a budget k, which is a non-negative integer, and let's ask ourselves the question whether it's possible to remove at most k vertices from our graph G in order to fall into our favorite class G. And this parameterized problem turns out to have interesting solutions or non-solutions to some of the well-known classes, which can be our favorite ones, right? So they admit nice solutions. And so let's have a look of the inclusion graph of some of them. So those are several subclasses of perfect graphs, where the arrow is resembling inclusion of classes. And what we know about this k-vertex deletion problem, and what was arguably the first result about it, is that bipartite graphs admit polynomial time algorithm after we fix k, so an FPT in k algorithm of vertex deletion. It's called out-cycle transversal most of the time. And we know also that chordal graphs, for example, are FPT, but on the other hand, it's been proved that perfect graphs most probably don't admit such an algorithm because they belong to the W2 class. The problem of k-vertex deletion is W2 hard for them. So there is still some space for coloring this picture. But why do we want to color this picture and see which classes admit this vertex deletion problems? We can have lots of motivation, but our main motivation is that the classes that you can see in the picture, some of them, maybe let me just color the things that we know, especially those permutation, comparability, and comparability classes are strictly connected to poset world. So comparability graphs, for example, are graphs, precisely graphs of partially ordered sets. So the same parameterized stuff like object deletion can be considered with respect to this order world, and those classes are very much related to it. So yeah, so generally solving this would allow us not only to understand those classes vertex deletion wise, but some other structures, combinatorial structures like posets. Okay, and what I would like to show you today is that this rectangle is actually blue. So there is an FPT algorithm for vertex deletion to bipartite permutation graphs. And well, having this problem in mind, we can ask ourselves how to tackle it, how to generally tackle it. So let me tell you one thing about generic approach to vertex deletion problems. I mean, how to achieve such an algorithm which allows to like delete vertices to obtain some graph. Let's focus on this hereditariness of our class. So being hereditary means close under vertex deletion, or as you will like close under taking induced subgraphs. And it's well known and celebrated that it can be characterized by a forbidden family of induced subgraphs. So all of these classes can be defined uniquely by giving a family of graphs that cannot appear as induced subgraphs, like minimal ones, connected and stuff. So when we view our graph class in terms of this forbidden family, then we can just try to hit every occurrence of a graph from this family, or of an induced subgraph from this family. And what is particularly good to know here, that if our forbidden class is finite, then we have always this FPT algorithm, right? Because if we had a finite class of forbidden graphs, then we can do this branching, right? Branch out every possible occurrence of our forbidden structure. Yeah, so more precisely, if in our graph class F, which is forbidden, we have at most graphs of say at most m vertices, right? Their number is bounded, so their vertex size is bounded. Then we can go over all m element subsets of vertices in our base graph. And if we find an occurrence of our forbidden structure, we simply branch over all possible removals of this vertex, and carry on with smaller budget, right? Because we have only budget k on the removal of vertices, which is an approach which is clearly exponential in k in our parameter, but it's polynomial in n. So it leads to an FPT algorithm. Either we run out of budget and we have still forbidden structures in every possible manner of deleting vertices, or we are able to delete at most k. So the generic approach would be to try to delete all the forbidden instances, forbidden copies of our forbidden graphs from our graph G. However, if the family is infinite, then we still need to do something more. We can only delete, reduce the graph without finite many of them. And this is nice. So for all those graphs, the forbidden families are infinite, so this approach doesn't work, but it works for pretty much every graph class defined by a finite F set.
Sorry, but can I ask a question?
Sure.
What does it mean? I mean, the graph is finite, right?
Yeah.
So what does it mean for the family? I mean, they have to be subgraphs of a finite graph, right? So how can there be infinitely many? abstractions?
Okay, so if we are trying to deduce whether our graph belongs to the class or not, we need to check whether it contains any of the forbidden structures. So if we have infinite number of elements of F, then we cannot perform it in general, yeah, in finite, in polynomial time, as which is polynomial with respect to n. Okay, because the n might get larger, and this class F may consist of arbitrarily large graphs. So when n is huge, we have more and more graphs to check, and they can have more and more vertices when we check it.
Okay, because it's the set of abstractions for the whole graph class.
For the whole
okay.
class. Yeah,
Sorry.
yeah.
Maybe it's good to see actually this on an example of bipartite graphs, where the abstraction set are all odd cycles, and you need to exclude all the odd cycles to get all the bipartite graphs.
Okay, thanks.
Thanks for the question. Thanks for the comment. Any other questions for the vertex deletion part? I mean, it's just an overview of what the problem is and how it can be generally tackled. And I think it will become even more clear if we switch to bipartite permutation graphs and try to apply this to this context. Okay, so what are bipartite permutation graphs? Before I answer the question in a proper way, let me answer it in a silly way, that those are the permutation graphs that are bipartite. And permutation graphs, as you can see here, are a hereditary graph class as a subclass of perfect graphs. So we can define them via forbidden induced subgraphs. We know the family for permutation graphs. This is the family. It consists of 9 7 vertex graphs and actually 18 7 vertex graphs and 14 infinite families of graphs, because apart from what's drawn here, we need to have all the complements taken of those graphs. So it's quite a large family, and it's quite hard to like grasp all those occurrences of infinite families at once. But when we consider bipartite permutation graphs, we need to add all the forbidden odd cycles to this family, and the only missing forbidden odd cycle is a triangle, as you can see, because we have all induced cycles of length at least 5 here. After we add triangle to this family, almost all of these guys would disappear, because almost everywhere in a graph or in a complement there is a triangle. Okay, so if we add triangle to this family, then the graph class defined by intersection of the two would be defined by the union of the forbidden sets, right? And that's what we are left with. So bipartite permutation graphs are precisely those graphs which don't contain induced cycles of length at least 5, a triangle, and this free sweet cute 7 vertex graphs called T2, X2, and X3. That's one way of defining them, which is proper for our vertex deletion considerations. But what's arguably the most important here, the most important thing here is that we can define this class in another way. And as this class is related to some orderings and posets, it turns out that this other way of defining bipartite permutation graphs is also connected to so. So say we have a connected bipartite graph, and we order one of its parts linearly. We say that this order has this green order here, adjacency property. If for every vertex from the other side, its neighbors are consecutive in our order, like this, and it holds for every vertex in U, right? U is the other part of our graph. And we say that it has enclosure property if for every pair of vertices here downstairs, such that one neighborhood is contained in the other one, it's like moved to the end. We don't have a situation like this, that one neighborhood is contained within the other one with non-empty difference here and here. Okay, so it's moved to the edge. So having these two properties of a linear order of one part of a bipartite graph in mind, we can state the theorem that says that the graph is bipartite permutation. Connected graph is a bipartite permutation graph if and only if we can find an order which has both enclosure and adjacency properties for one of its parts, and symmetrically for the other one, right? So after we sort the vertices in W so that the neighborhoods of vertices in U behave in a nice way, we can do the same to the vertices of U. So we can think of it as a pair of orderings of the bipartite classes, bipartition classes. Okay, so another view, like more maybe intuitive, is that bipartite permutation graphs are precisely those graphs which are embeddable into the opposite edges of a rectangle, say paper rectangle strip, in a way that neighbors of vertices from the bottom edge satisfy enclosure and adjacency properties on the top edge. So they are together and shifted. If they are included in one another, then one is shifted from only one side. And the same holds from bottom to top. So this enclosure and adjacency properties are here. And bipartite permutation graphs are embeddable in these strips of paper. Okay, so those are bipartite permutation graphs, and now how to tackle them. So what we do, actually we, referring to this branching technique, we can reduce our class to, we can remove some finite subcollection of those forbidden graphs, say all of them and some small cycles, and we are left with a graph which may have long induced cycles, but nothing else from those. Okay, so this is our step in the proof to define such a class after removing some finite number of graphs from here. And we call this class almost bipartite permutation class. And we prove a structural theorem about this class. And this allows us to say that this k-vertex deletion has about 9 to k times n to the 9 time algorithm. So an FPT1. And we can also derive from the same approach by slight modification and 9 approximation algorithm for vertex deletion polynomial time. And how to achieve this? Let me introduce to this almost bipartite permutation graphs. So again, via forbidden induced subgraphs, and this almost refers to bounding the length of forbidden cycles. We forbid only small cycles of length at most 9. And it turns out, and we prove this, that we can also have an equivalent definition of almost bipartite permutation graphs via this ordering stuff, via this poset stuff. And the property, the definition here would be that those are precisely graphs which are embeddable in either a cylinder, so not a rectangular piece of paper, but glued together piece of paper, the cylinder, so that the bipartition classes become ordered cyclically, or a Mobius strip. So we also glue together this bipartite permutation graph, but we have twist it while gluing. Okay, so yeah, one more time, almost bipartite permutation graphs would be a graph whose neighborhoods are local, like they are on the other side of the strip here locally, and satisfy this enclosure and and adjacency properties, but the global structures can be organized in this cyclic glued together way. And the long holes that we still can have in our graph are precisely the holes that go around here and here. And this also can be proven. So now this almost, in this definition, becomes almost of the following sense, that when we cut out some small piece of our strip and unfold it, then what we get is a bipartite permutation graph. Okay, we cut out a piece large enough to kill all the edge connections between two sides. Like here or like here. And after unfolding, we get a bipartite permutation graph. And knowing this makes it really much more easy to hit all the remaining forbidden graphs for bipartite permutation graphs, so all the large holes. Now, after we know that we can remove only a small number of vertices somewhere in order to kill all the remaining long holes. Yeah. So basically, the concept of everything is to prove that this almost implies this almost, this understanding of almost being bipartite permutation graph. And in a little bit more detail, how to achieve these structures from assumption that we have no induced subgraphs of those given types. Let's see. Okay, so first of all, note that we can consider our graph to be connected. Okay, so if we have a disconnected graph, we can look at each part separately, and we will build this Mobius strip or cylinder structure inside each connected component. Okay, and now let's take an almost bipartite permutation graph, so a graph defined as here, which is not bipartite permutation graph, so we have these long holes there. So what we can prove is that every such hole induced cycle is a dominating set in such a graph. Okay, so remaining vertices can be organized around any hole which remains there. After we take the shortest hole, we can say it's of length 10, as in the picture. We can organize the structure of our graph around this shortest hole that we pick. And let's draw it in the picture like this mimicking this bipartition classes. If it was of odd length, then we should be mimicking this half twist in a Mobius strip, but this is easier to draw. And more precisely, we can, for the shortest hole, say that every other vertex in the graph is connected either to a single vertex of the hole or two vertices that are one apart. So the incidence to this hole can have only two types. And therefore, all the vertices in our graph decompose into this type of incidence classes. So we are getting more and more structure now. Now, after we have these classes, we can prove that the neighborhoods of those vertices are in fact local. So contained in the nearest classes on the opposite side of our picture, because if there were neighbors who are far apart from us, we could have shortened our shortest hole. That's basically the idea. So if we have an edge which connects two places in the graph which are far apart, we could make our longest hole, shortest hole even shorter. So we have these local neighborhoods, and these local neighborhoods allow us to rearrange the vertices inside those classes in order to get this adjacency and enclosure properties, but locally. Having viewed these vertices like only with respect to the part of graph which they are contained in. So forgetting about the antipodic, the opposite part of our strip. And this, after having this ordering of vertices introduced, which is either a pair of cyclic orderings or one cyclic ordering if we have a Möbius strip, we are basically done with this almost definition via ordering of vertices, right? Because now if we remove actually four such neighboring classes, we can kill all the connections between left and right side, because the neighborhoods could have, as you can see, the neighbors can be in 2, 1, 0, 1, 2, at most 2 classes apart on the other side. Yeah, so this guy may have the furthest neighbor here. And after unfolding, we get the bipartite permutation graph. And what is more, we can say that the minimum size, minimum whole heating set, so the set we need to remove, set of vertices we need to remove to get rid of all the remaining holes in our graph, the long holes, can be, is actually contained within a local frame as well. Here, I call this local frame a window. So now, knowing this, that the remaining set of vertices to remove, if it's possible to get rid of all remaining long cycles, we know that it's possible to get rid of them in minimum number of vertices within this short, this narrow window, right? So we need just to go through all possible windows and find a minimum separation, so vertex separation, separating set within such a window, separating left side from right side. Yeah, and such a separation can be done by classical max flow min cut. So after we take a local window of, say, width 5, we can adjoin source to one side, sink to the other one, do some stuff technical inside, and find the minimum size vertex set separating left side from the right side. So allowing us in the minimum budget to kill all remaining holes in an almost bipartite permutation graph. And after we add it up, we get our algorithm, for now described roughly by pictures, and I will recap the structure of it in a minute once again.
So if I may ask a question here, do I understand correctly that if you have an almost bipartite permutation graph with no short holes, then it's polynomial time solvable to find the smallest heating set for the remaining holes, and you can solve the problem in in polynomial time. Okay, so essentially on high level, it's like you prove that you almost already have a bipartite permutation graph in this structural definition, but the strip of paper can be wrapped into either a cylinder or a Möbius strip. And what you argue is that you will, the best solution is just to cut it locally somewhere along this wrapping.
Yeah, that's perfectly right. That's exactly what it is.
Okay, that's pretty cool. Mm-hmm.
Yeah, so in order to have this polynomial time algorithm, we need to know that this is local, right? The minimum heating set. So we can rush through all the possible windows. There are polynomially many of them, and apply this flow algorithm inside each of them, which is also a polynomial time algorithm. And we find the minimum vertex heating set of the remaining long holes. Okay. So once again, to sum it up, how does the FPT algorithm work? We are given the instance, we have a graph G and the budget K. And first of all, we get rid of all small forbidden subgraphs by branching. So after we meet some forbidden structure, we branch over all possible removals of one vertex and proceed recursively with smaller budget. Yeah, and here by small forbidden structure, I mean a cycle of length at most 9 or one of the 3, but for 4, right? So 3, 5, 6, 7, 8, or 9, or one of the 3 small graphs. And either we run out of budget in every case and still have some forbidden structures inside. So we cannot reduce to almost bipartite permutation graph, or we get an equivalent set of instances. So we have an answer yes in the general problem if and only if at least one of the answers we get is a yes. And as I told you before, because our our small forbidden graphs are of bounded vertex size, here 9 is the largest size of vertex set. We have this branching tree of size at most 9 to the k, and in each node we perform looking for forbidden structure of size at most 9. So all in all, we get this n to the 9 times 9 to the k as given in the statement of the theorem. And after we reduce this to this set of small instances, say we have this instance with smaller budget and almost bipartite permutation graph, we know that each connected component has this structure of a cylinder or Mobius strip. And so we can build this structure along the shortest hole, define these orderings, and then go through all the windows, turn them into flow networks, and apply flow algorithm to find the minimum size vertex separator from left to right. And depending on whether our minimum size vertex separation added among all the connected components have size lower or greater than our remaining budget, we conclude with a yes or no answer here. Yeah, and due to this going through windows and applying flows, this turns out to have complexity about n to the 6. But let me not dive into details why in our proof is 6, not 5 or 7. Okay. So that's a way to turn an arbitrary graph into a bipartite permutation graph. Which is
sorry. Can I ask a question as well?
Sure.
So why 9? I mean, why do you have to? Is there an easy argument? Why do you have to define these almost bipartite graphs this way, and the proof doesn't work if you define it differently, like more cycles or less cycles, or like less cycles maybe?
Yeah, thank you for the question. This 9 comes from some technical details hidden in the proof. We need the assumption that the remaining cycles are long enough in order to have this proper notion of localness, say. So, for example, if we consider these wide windows of width 5. We don't want the remaining classes to be too close to one another, because then we could have some non-trivial neighborhood relationship here and here. And we cannot so simply say about the left side and the right side, because, yeah, for example, if the number of classes here were smaller, then they could be connected somehow. To answer the question, this 9 comes from the arguments hidden in proofs of all these structural lemmas, and it are required in order to for the reasoning to work. Is basically connected with this neighborhood being local, but still being like of some constant size. And we want the right neighborhood of our local window and left neighborhood of our local window to be not connected, to be disjoint.
Thanks.
But it's possible that some refinements here and there and more careful arguments could yield a smaller number here. I mean, I'm not saying that it's not possible, but yeah, but that's what we obtained from our
okay, so you didn't rule this out, that it would also hold for like 8 maybe or something like this.
Yeah. mean, the statements that are provided work for 9 and probably not for 8, but probably some more refined statements would work for a smaller number. Okay. Any further questions here for the structure of algorithm, or should I explain?
This approximation algorithm that you mentioned, you just take the obstacles, the small obstacles greedily, I guess, and then apply. Yeah. Okay.
Yeah, precisely. Yeah. Yeah, that's why I wanted to focus on this one here. So I promised to give you the flavor of how to use the forbidden structure to obtain results as ours. So let's have some proofs. I try to find the nice ones. So for example, why are all holes dominating in our graph? So to be precise, let's have a connected almost bipartite permutation graph, which is not bipartite permutation. So we still have some long holes of length 10 and above, supposedly. And why everything happens around these holes? Why cannot we have a vertex which is of distance 2 or more of our arbitrary induced cycle? So suppose we have, right, some hole and a vertex which is of distance 2 but not 1. Okay, so as it's of distance 2, we have no edges from here, from the bold guy to the cycle. Okay, and now we can condition on where are edges and where are not. So we don't have triangles in almost bipartite permutation graph, so those are non-edges. And now either we don't have any of the two edges and we find a forbidden structure here, which is this T2, 7 vertex graph, or we have at least one of those edges, say this one, right? And now we can find this forbidden structure here. This is a square with 3 hairs, say. So if we had such a distant vertex, it would yield a forbidden structure. So holes are dominating. Let's have a bit more challenging one. So about this 2 types of incidence to shortest hole, right? We have this shortest hole, remember, and we now say that every vertex is incident to only one of the nodes, or 2 which are or distance 1 apart. So take the shortest hole here. 3, 4, 5, 6, 7, 8, say 10. Okay, and take any other vertex in our graph. Okay, so we know that this hole is dominating, and our graph is connected almost bipartite permutation graph. So there is at least one connection, at least one neighbor, and now it's either only one is cool, or there is another one somewhere. Okay, so let's take the clockwise first, the earliest one, right? And if it's here or here or here, if we have 2 or more vertices here apart, we get a shorter hole, which is a contradiction of with this C being the shortest one. Maybe, but for this situation, yeah, where we have a hole, the Pacman hole of the same size. But either way, we have this closer neighbor of distance 2 apart, and it's cool for now. So either we finish this, or we have another neighbor, and now every other neighbor should be distance 2 apart. So we get like this, say, partially subdivided wheel here, and in this partially subdivided wheel we can find the third forbidden small graph, like this, for example. given that this hole is long enough, right? And that's one of the places when this bound of the length of the holes that we forbid in almost bipartite permutation graphs plays a role somehow. Okay, and I have two more statements prepared for you, but I'm afraid we're slowly running out of time. So maybe if some of you are interested in details of this proofs. So first one is that the holes are homotopic to the shortest one. So as I said, they go around this glued strip. The other one is that this minimal hole heating state, which is a crucial one, are in fact local and not spread out on the entire strip. That was a long sentence. Then I can show it later. And now let me just say a few words about where this could go further. And let's go back to the picture we've seen on the first slide. Note that this picture is actually a poset, right, of this partial inclusions of graph classes. And this word poset is crucial here because, as I said, those graph classes are highly connected to posets, and if we restrict an input to be a poset itself, so basically in graph sense a comparability graph, right, then we get a vertex deletion problem for posets, which can be approached now having some notion of what happens, some intuition of what happens in bipartite permutation graph. We may try to extend it to these, which are seemingly more difficult to say something about, because as you've seen, the forbidden family for permutation graphs is quite a mess, right? So yeah, so first of all, try to do something about vertex deletion to the three remaining graph classes in the picture, maybe via defining this almost graph class graphs. And switch to the world of posets. Actually, these bipartite permutation graphs translate to, I guess, two-dimensional posets of height at most 2. So it's a structure which is also perfectly fitting in the other combinatorial context than the graph one, right? And it gives us the direct result on those two-dimensional posets of defined height, and we can try to extend them to like larger height or no height at all involved, right? So just permutation graphs or something. Okay, I think that's pretty much everything I wanted to show you. So thank you very much for the attention, for the questions, for the comments. And I'm happy to answer any further questions if there are. Thank you.
Okay, so thank you, Łukasz, and can we maybe unmute ourselves and give an applause? So in 3, 2, 1, 3, 2, 1. Okay, so are there any questions or comments or remarks?
Or likes or subscriptions.
So if I understand you correctly, like you take a look at the shortest cycle in that almost bipartite graph, and if it's like even, you try to embed it in the strip, like in the cylinder, and if it's odd, then it somehow works out as maybe a strip.
Right. Precisely.
Yeah. Mm-hmm. But like I had a problem with that in like, I'm not exactly sure, but in your like first definition of like the first definition of a bipartite graph of the embedding in like the flat strip, there was a thing that the vertices on one side, like you describe the intervals of the neighborhoods of the vertices of one side on the other side. And how does it translate into the world of Möbius strips?
Okay, thank you for the question. Let me try to make it more precise, the definition here. So this embedding in Möbius strip we define as okay, so as a linear, as a cyclic ordering of the entire vertex set. Okay, such that if we remove 2 consecutive classes here and 2 consecutive classes here, they are indexed here, then after unfolding, we get this bipartite permutation graph. So this one cyclic ordering then breaks into 2 separate segments. Okay, and our definition of, I mean, if we talk about neighborhoods, then we don't care about the other side of the graph. So we can, we have this ordering inherited from this large cyclic ordering after deleting something far apart, far beyond our consideration scope. Here we are locally in this place, and this allows us to say about the other side, because we remove something on the other side of the strip, and we get these two orderings.
Okay, thanks.
Thanks.
So as a small remark, maybe I can add that most of this stuff were done at most around a year ago in a workshop in Krynica. So.
Yeah, I would like to also add here, probably it's both the speaker and Karolina should not are too polite to say this, but this paper was presented at IPEC last year, and it won the Best Student Paper Award there. And Best Paper Award as well, as far as I remember, right?
Yeah.
Karolina, Łukasz? Yeah, okay, so sorry for that. I'm terribly sorry. Both the Best Paper Award and the Best Student Paper Award.
Wow, congratulations.
Thank you.
Well, if you have a Möbius strip in your paper and such a cool drawing, then
yeah,
I guess this qualifies immediately. Yeah.
Those green those green drawings on the right are in the introduction, and I think it's the strongest point.
That's why they're in the introduction, but they're not green in the paper.
Okay, so if there are no more questions there, maybe we can thank Łukasz again.